Good day, grade 12 learners and teachers. Just a special greeting to learners at Pelutuna under the leadership of Rapadu and Mokabe. Welcome to today's mathematics lesson. My name is Mr. Shong. This lesson is brought to you by the Gauteng Department of Education in collaboration with the Saibono Discovery Center. Right, good people, today we are going to be looking at reduction formulae, identities, and the general solution. This is the continuation of last week's lesson. Right, let us look at the objectives for the current lesson. By the end of this lesson, you should be able to solve problems that involves the reduction formulae where compound angles and double angles are utilized. You should be able to solve problems involving numerical reductions, some of those leading to special angles. Should be able to understand additional formulae used in proving identities. I'll be taking you through those additional formulae. You should know them and you should understand them. They are very helpful when you prove identities. You should know how to prove identities where compound and double angle formulae are applied. Should be able to understand the concept of the general solution, as well as to know the different types of those general solutions. So I'll be taking you through step by step the different types of those general solutions. And you should note that we are going to be using the quadrant method. We are aware that we can use the quadrant method and we can use the graphical method. So for the purpose of this lesson, we will be using the quadrant method because that's what most teachers are using. And then we should be able to solve questions involving the general solution where a compound or double angle formulae are used. Right? Obviously, we can refer to the CAPS document as well as the exam guideline on those stipulated pages there, just to check the scope within which we should cover our trigonometry. Right, the knowledge that you should be coming with to this particular lesson. I think we've worked in the previous two lessons of trigonometry. We've been working on the knowledge that you'll be needing also today. So it's continuation, good people. Right, we should know how to define trigonometric ratios using the sides of a right angle triangle. Should know how to define trig ratios in a Cartesian plane. Should know our reduction formulae, the core functions, the negative angles, and the multiple rotations. We should understand our special angles, our basic identities. By basic identities, we are talking to the sine squared of theta plus the cosine squared of theta, which is equals to 1. And we are also talking about the quotient identity, the tangent of theta, which is the sine of theta divided by the cosine of theta. Those are the basic identities, right? We should know how to apply a compound angle formula to solve problems. That's what we dealt with a lot last week. We should also be able to apply the double angle formula to solve problems. That's what we dealt with again as well last week in detail. Right, now we look at the baseline assessment. This baseline assessment is looking at the concept that you've already covered in grade 11. So I am going to actually give you 5 minutes just to go through the baseline activity, just to check yourself whether you are ready for this lesson that we have just started. So I'm giving you 5 minutes for the baseline assessment. Your 5 minutes time starts now. Right, hello and welcome back. I hope you were able to go through the baseline with success. Remember, we are also available on our WhatsApp interactive number, which is 0647488913. I think it's popping at the bottom of your screen. You can ask us any questions that are related to today's lesson there, and we'll be able to assist you. Right, let's look at the solution set for this a baseline assessment. If you look at this, it is an identity that infuses the reduction formulae there as well as the core function. So let's go through the solution set for that. Right. First things first, if we look at the left-hand side, because it's an identity, we need to isolate the left-hand side, work on it, and then try to prove that it's equals to the right-hand side. But at times, you are required to isolate the left, work with it, simplify it, and then work with the right-hand side, simplify it, and then from there you find that the two sides are equal. Right. Now, let's go through here. Now, if you check here, because we have the cosine of 180 minus theta and 180 minus, if we are to look at our cast diagram here, sine theta, the tangent of theta, and then the cosine of theta there. We have that this is 180 minus theta, this is 90 minus theta, this is 180 plus theta, this is 360 minus theta. You can see there I'm not including the 271. Now, obviously here, if we are to look at this, the cosine 180 minus theta is in the second quadrant, and the cosine in the second quadrant is negative, so that reduces to negative cos theta. And obviously you will get a mark in the exam, you get a mark for all the reductions that you've done. So a mark for each reduction that is done there. Right, let's look at the second one. Sine of 360 minus, you can see 360 minus theta is in the fourth quadrant, and in the fourth quadrant only cosine is positive, so the sine would be negative there. You get your second mark. And then we look at the third one, the tangent of 180 plus theta. 180 plus theta is in the third quadrant, and if you look at the third quadrant, you can see only tan is positive, so this comes back as a positive trig ratio. And then from there we check cos 90 minus. If you look at 90 minus, it is actually in the first quadrant. In the first quadrant, all the trig ratios are positive, but the cosine changes to a sine, so we get a mark for changing the cosine to a sine. And then from there, the last but not least, we have 180 plus. 180 plus is in the third quadrant, and in the third quadrant only tan is positive, so sine should be negative there. Now you can see that there are like terms here on the numerator, or like trig ratios on the numerator as well as on the denominator. So we are going to divide there. We are going to divide. So when we divide here, you can see that the cosine, or rather the negative sign and the negative sign, will divide out, and we change the sign to a tangent to what? Sine theta over cos theta, which is the basic identity that we spoke about, changing tangent of theta to sine theta over the cosine of theta. And then this should then also divide, and then you should also get that this as well should divide, which means that you'll get an answer of -1, which is obviously the same as the right hand side there. So that would conclude what you had to work with. So if you look at this in terms of mark distribution, you would see that here you'd be getting, for this step, you should be getting 5 marks, and then for this step here, you should be getting a mark for changing this to sine over cos as well as dividing. So you should have 2 marks here, and then if you combine this, then it gets that this problem can be for for 7 marks. And this is not a difficult problem, but it needs you to know and master your cast diagram. Right, let's move on now to start today's lesson. We are starting that with summarizing the reduction formula using the cast diagram. Now, I am going to take you through this cast diagram that you know, that you've worked with from grade 10, but you've added the reduction instructions now in grade 11. We are going to continue with that also in grade 12. Now, if you check our cast diagram, you can see that all the trig ratios are positive in the first quadrant. In the second quadrant, only sine is positive. In the third quadrant, only tan is positive. In the fourth quadrant, only cosine is positive. Now, if you check here, it's from 0 to 90. So the angles that are in the first quadrant are actually less than 90. That is why the instruction here is 90 minus theta, because we are talking to angles that are less than 90. Now, if you move to the second quadrant, we get what we call the obtuse angles. The obtuse angles are greater than 90 but less than 180, because this line here represents 180. So we are moving from 90 to 180. So the angles in the second quadrant are less than 180. So we can use 180 minus, because they are less than 180 but greater than 90, which means we can use the 90 degrees plus, which is a core function instruction there. Now, moving on to the third quadrant, we have what we call the reflex angles, angles greater than 180 degrees but less than 360 degrees. Now, if you look at that, you can see that now these angles are greater than 180 degrees. So that is why we can change the reduction instruction there to 180 plus in the third quadrant. Now, if you go to the fourth quadrant here, you can see that now, if you locate the way that I'm moving with my quadrants there, I am moving in an anti-clockwise direction. That is what we do in trigonometry. We move in an anti-clockwise direction. Now, if you check on the fourth quadrant there, it's a reflex angles greater than 180 but less than 360. So you can see that it's 360 minus, because we are between 270 and 360. Obviously here there can be an instruction for 270 plus and 270 minus, but I am not going to entertain that. It is not within the spirit of caps to look at the 270, right? Now, also here you can, if you go for the second time, you can have now what we call the multiple rotation now, which means this quadrant will then be 360 degrees plus theta, because it's now beyond a revolution. It's beyond 360 there. Also, if you notice here, I also have here a negative angle there, negative theta, because we are saying if you are measuring angles in an anti-clockwise direction, and this is angle theta, you can go the same degree. You can go the same degree, but going in a clockwise direction. If you are to do that, you are going to get now the reflection of this particular angle along now the x-axis. The reflection along the x-axis, which then gives us the negative angle. So we get that this is negative theta, and you can see that this negative angle is located in the fourth quadrant, and in the fourth quadrant only the cosine is positive. That is why it is only the cosine of the negative angle that becomes positive, because the negative angle is in the fourth quadrant and only the cosine is positive in the fourth quadrant. Now, we need to note here that any multiple of 360 can be added or subtracted from an angle if necessary. I'll be doing that a lot. Addition of 360 and subtraction of 360. It can be done to help us with working with negative angles, and also to help us with working with multiple rotation, where you have that you've rotated more than 360 degrees. Right. I think we've just summarized our reduction formula there. Let's now go and apply the summary that we just did to problem solving. Right. Now, looking at this example one, we are making use of the reduction formulae. Now, please note, as we use our reduction formulae, it is important to be in position of the cast diagram. It is important to be in position of what? The compound angles, the a double angle formula, which would be there in the formula sheet, but the cast diagram will not be there. So you should be able to write down your own cast diagram. Right, to start off with the solution set for this, we will actually be looking at our tools here. Our tools here, you can see that it is the, what you call the formulas there. We're supposed to also have the cast diagram there, but it's fine. Let's just work on this now. We have that this is the cosine of negative x, which is the negative angle, and we know the negative angle is in the fourth quadrant, and then we going to have that this is the cosine of 360 plus, the cosine of 360 plus, this is in the first quadrant. And then we have this cosine of 90. This is also in the first quadrant. And we have the sine of 180 plus. Remember, it is all sine theta, tan theta, and cosine theta. If we look at this, you can see that now in the first quadrant, we said it's 90 minus theta. This is 180 minus theta. This is 180 plus theta. This is 360 minus theta. This can also be 360 plus theta there. Now, if you check, we said the cosine of negative x is in the fourth quadrant because we are saying also we have negative angles in the fourth quadrant. And cos is positive in the fourth quadrant. That is why here we will present a positive cosine x. Second one, cos of 360 plus, it is also in the first quadrant. It is in the first quadrant, and in the first quadrant all trig ratios are positive, so this would be a positive cos x. Then we look at this cosine of 90 minus. Remember, when we see 90, we know that the cosine changes to the sine and the sine changes to a cosine. That is when we have 90 degrees. But first we need to locate the quadrant. It is in the first quadrant, and cos is positive in the first quadrant because all trig ratios are positive in the first quadrant. So this becomes a sine of x because for 90, the cosine changes to the sine. Right, and then the last one, 180 plus. 180 plus is in the third quadrant. And if we go to the third quadrant, we see that only the tangent is positive in the third quadrant, which means all the other trig ratios are negative. So that is why this became negative sine x. So currently, as it stands, you have about 4 marks. If this question was for 6 marks, you already have 4 marks, good people. And that 4 marks is not difficult to get. So please make sure you practice your reductions. Right, obviously if we simplify that, we can multiply the cosine and the cosine, it becomes the cos squared of x, and then the sine and the sine becomes the sine squared of x, and we are seeing something that we are familiar with. Cos squared minus sine squared. From the formula sheet, you can see that we are operating in this space. We have a double angle. We have a double angle. That is actually an expanded form. We have a double angle in expanded form, and right now we need to then congest so that we further simplify. So we are moving backwards from the formulas that are given there. So we congest that to the cosine of 2x. So we were going to actually get a mark for that. So if this question was for 5 or 6 marks, if it was 6 marks, then we're going to give a mark for the simplification there and give a mark for the congestion of the double angle. And remember, the congestion comes from the formula sheet, which means every time when you do your trigonometry, your formula sheet should always be there. Right. I hope you understood how we worked with that problem. We want to move on now to the first activity now that you have to do here on the reduction formula. I am going to give you just 4 minutes here, 4 minutes to try and work with this problem. 4 minutes is enough, and your 4 minutes time starts now. Good luck. Right, hello and welcome back. Hopefully you were able to solve that question with ease, or if there were challenges there and there, hopefully we can discuss them together now. Right. Now, if we are to locate this, remember I said the most important tool to have here is the CAS diagram together with the formula sheet. Right, let's see now how we can go about that. There is my CAS diagram there, and there is my formula sheet there that I'm going to be using. So it's important to have all those tools with you to assist you to be able to locate the correct quadrants. Now, if we check the first one, this is in the first quadrant. You can locate it in the first quadrant. And then with negative angles, you can see that here, the numerical value here is negative, and the numerical value should always be positive. If it's not positive, then it means you have what we call a hidden negative angle. So the numerical value there is negative. So this is a negative angle, so we can locate it in the fourth quadrant. We can locate it in the fourth quadrant. And then we have this one here, which is 180 minus. You can see 180 minus, it's in the third quadrant. There it is there in the third quadrant. So this is in the third quadrant. And then we look at 1080 plus x. So this is a multiple rotation here. It's a multiple rotation. For now, we are not sure of the quadrant. We'll just say it's an angle that is greater than 360 degrees. There is methodology to be able to work with that. I'll be taking you through that. Now, let's start with the first one. The first one here, it's the cosine of 90 minus x. This should reduce to the sine of x, because in the first quadrant, cos is positive, and cos changes to sine because of the existence of the 90 there. We use what we call the core function formula there. Now, looking at the second one now, the second one, allow me to just write it on the side here. We have the sine of negative x minus 180 degrees. I said to you, it's a hidden negative angle. So we can take out a negative here. This becomes negative into x plus 180 degrees. So using the commutative property, this would be the sine of negative 180 degrees plus x. Now, if we check, because of this negative angle there, we are saying we are on the fourth quadrant. So that is the first thing that we are going to address. So if we address that, we will say sine in the fourth quadrant is negative. So this becomes negative sine of what? The angle remaining here is 180 plus x. So this can undergo a further reduction. Because this is 180 degrees plus x, where is 180 plus x in the CAS diagram? It is in the third quadrant, and sine is negative in the third quadrant. So this becomes negative of negative sine x, and this would become what? A positive sine x. You can see the correct mathematics there. It says to us we need to take out the negative, then pick up that we have a negative angle, apply our knowledge of negative angles to say they are giving us positive cosine, because cosine is positive in the fourth quadrant. So we get that all the other trig ratios will be negative when we look at the negative angles there, because they are in the fourth quadrant. So we will get negative the sine of that particular angle. But we can see we have a further reduction of 180 plus, which is in the third quadrant, and sine is negative there. So it's negative multiplied by negative, which is positive sine theta there. Now, I have an alternative way in which you can do this. Remember when we started, I said you are allowed to add or subtract 360 when necessary. You are allowed to do that to try and negate the problems that negative angles bring along to try and negate the problems that multiple rotations bring along. So what we're going to do here to solve this, we can say because it's a negative angle, this numerical angle is negative, we can add 360 to it. So what will happen here? You will be getting, allow me to squeeze it somewhere here. Let me just squeeze it somewhere here. You will be getting here, you have the sign of negative x minus 180. You will add 360 to that, but you won't be writing it explicitly. You will just add it in your calculator and check what you get. You will get that this is the sign of what? Negative x plus 180. So this is just the same as what? The sign of 180 degrees minus x. So 180 minus x, where is it? It is in the second quadrant. And in the second quadrant, sign is positive. So this reduces to just the sign of x, which is the same as what we got there. So it's another way, it's an alternative approach to working with what? Negative angles there. We can just add a revolution, right? So now let's look at that. We said this would also be positive sine x. Now, if we look at the cosine of 180 minus is in the second quadrant and the cosine is negative in the second quadrant. So this is plus negative the cosine of x. And then now we are looking at a multiple angle. We have 1080. Because it's multiple rotation, you can subtract 360 until you get an angle that is less than 360. Now, if I check here in my calculator, I have 1080. If I subtract 360, I get 720. If I subtract 360, I get 360. So this would be the cosine of 360 degrees plus, it becomes what? The cosine of 360 degrees plus x. And 360 plus x, you can see it is in the first quadrant and all trig ratios are positive there. So this becomes positive cos x. So that is the first step. And remember, you will get 1, 2, 3, 4 marks by just performing those reductions there. Right, let's move on and see the solution set now coming through. Now, if we look at the first step, obviously, I have written it down, the sine of x, negative cos x, then we multiply the two because they are actually like terms. So if I multiply, I get the sine squared of x and the cosine squared of x. This looks like it is a double angle that has been what? That has been expanded. It is the expanded form. But if you check, it looks like this. It wants to look like this one on the formula sheet. But the only problem here is that when you compare the two, you can see that the one that is written here, the sign is positive, the cosine is negative. But the one that is on the formula sheet, the cosine is negative, the cosine is positive, and the sign is negative. So you can see there's a change of sign. There's a change of sign. So we're going to use the change of sign approach, where we take out a negative sign as a common factor there. So we're going to take out a negative. If we take out a negative, then we get that there is a change of sign of the trig ratios. Now, comparing this with that, you can see it looks exactly the same, which means that we can now move on to that part here, to the double angle there. So if we simplify that further, we can see that we get negative the cosine of 2x. Negative the cosine of 2x. So that is how we were supposed to approach that particular problem. I hope that you are still with me. Right, let's move on now. Remember, if you are not with me, please ask those questions on our interactive WhatsApp number. It is popping at the bottom of your screen there. You can see it. Please interact with us there and ask questions based on the lesson that is ongoing right now. Right, let's move on to the next slide here. Now we look at it, what we call the numerical reductions. What are numerical reductions? Numerical reductions are reductions where our angles, where our angles now are given in terms of what? Just numerics. It's just numbers. There is no theta, there is no alpha, there is no x, no variable there, just the numerical values. So what is it that we need to do when we are presented with numerical angles? We are going to locate the quadrant where they are found, because we want to reduce. In trigonometry, good people, the main focus of trigonometry is to reduce all angles and ensure that they are acute. So that is what we always try to do in trigonometry, is to work with acute angles. So if you look at the angles that are given there, it's 345, 255. Those angles are not acute, they are both reflex. So we need to reduce them so that they are acute. How do we do that? We make use of the reduction formula. How do we use the reduction formula? We go to our cast diagram, we locate the quadrant where the numerical angle is found, and we then write it in terms of the reduction instruction in that quadrant. Right, let's go through that. Now, obviously, I have indicated to you that the tools to use here would be the was supposed to be the cast diagram here, but it's not there. Made a mistake there. It was supposed to be my cast diagram there. Now, I want us to then look at this. I need to then redraw. We have that this is all 90 minus theta. This is the sine of theta. This is 180 minus theta. This is the tangent of theta. This is 180 degrees plus theta, and this is the cosine of theta. This is 360 degrees minus theta. What I am going to be highlighting there with an asterisk are what I refer to as the reduction instructions. So once you've located the quadrant where the angle is, you need to apply the reduction instruction in that particular quadrant. Let's check 345. 345 greater than 108, greater than what you call 270 degrees, but less than 360 degrees. So we know that this should be in the fourth quadrant. 255 is also it's less than 270 but greater than 180, so this should be in the third quadrant. Now we know the instruction in the fourth quadrant is 360 minus theta. The instruction in the third quadrant is 180 plus theta. So we'll express this as the sum of the angles, or the difference of the angles, where the reduction instruction there is utilized. So if you check the first step here, we are going to say, okay, since it's in the fourth quadrant, we're going to find an angle that we can subtract from 360 to take us back to 345, and that angle is 15 degrees. So we can write 345 as what? 360 minus 15 degrees. And then we want to write also 255 as a compound angle. We said it's in the third quadrant, the instruction is 180 plus, so we are going to check the angle that we can add to 180 to get 225. How do we get that angle? We'll say 255, I mean minus 180, it gives you 75. So you know you need to add 75 to 180 to get 225. So after having done that, we can see that now we've written this as the compound angles that can actually lead back to the values that we had originally. Now we can apply our reduction formula here. If we reduce 360 minus, it reduces to minus sine 15, because 360 is minus is in the fourth quadrant and sine is negative in the fourth quadrant, so we get minus sine 15. You can see now 15 degrees is acute, so we were successful in being able to reduce the angle to an acute angle. And then we go to this, the second one, 180 plus is in the third quadrant, and in the third quadrant, sine is negative. Only tan is positive, so this reduces to negative sine 75. Now, we want to continue with this, we can see that we have sine, but there is no relationship between the two. We cannot multiply them together because the angles are different. However, one can also pick up that since we have sine of 75 here, if we want to write it in terms of cos, or we want to find the complement of 75, this would be the same as what? The cosine of 90 minus 75, because cos of 90 minus changes to sine 75. So if we are to write that as the cosine of 90 minus 75, like that, or 90, or rather, we can actually, let me take this away, we can actually write down the sine of 75 there as what? The sine of 90 degrees minus 15. Sine of 90 degrees minus 15. I made a mistake with this one. Sine of 90 degrees minus 15. So if we subtract 15 from 90, we get 75. But the sine of 90 changes to what? Cos 15. So this thing can be written as cos 15 using what you call the cofunction. So now if you look at that, we've changed that to cos 15, and the positive, negative and negative, when we multiply them, they give us a positive. So from there, we can see that it looks more or less than this. Sine alpha cos alpha, sine 15 cos 15. It's just that we are missing this 2. We are missing the coefficient 2. So we are going to strategically introduce the 2 by writing this as half times 2, because half times 2 is 1. So if we write that as half times 2, you can see that it's now 2 sine 15 cos 15, which is exactly now looking like that now, which means we can then apply the conjunction to form our double angle. So this becomes half the sine of 30. Where did we get the sine of 30? We got it from the fact that 2 sine 15 cos 15 is the same as what? The sine of what? Double the angle, double 15, which is the sine of 30 degrees. That's where we got the sine of 30 degrees there. And then sine of 30 is half using the special angles. And then when you multiply the two, you get 1/4. Right. Let us move on now. Let us move on. We have an activity where you need to apply your numerical, or your knowledge of numerical reductions. I am going to give you 4 minutes as well to work quickly with this particular activity. 4 minutes, or let me make it 5 minutes for this particular problem. Please work on it as quickly and as best as you can. Your 5 minutes time starts now. Right, hello and welcome back. Hopefully you were able to work around this. Let's go through it together. Um, Obviously, we will need our class diagram there. Let's start. You can see 190. It should be in the third quadrant. It's in the third. And in the third, the instruction is 180 plus 170. It's in the second quadrant because it's less than 180. In the second quadrant, what is the instruction? 180 minus, and then 290. 290 is in the fourth quadrant. What is the instruction in the fourth quadrant? 360 degrees minus. So that's how we're going to start. Right, looking at that, you can see I've infused my reduction instructions. Remember, there is no mark for this. You don't get any mark here. There is no mark for doing that, but it helps you to see the reduction instruction explicitly so that it can be easier for you to reduce. Now, let us then reduce this. 180 plus is in the third quadrant and tan is positive in the third quadrant, so we are left with the tangent of 10 degrees. And then 180 minus cos of 180 minus here is in the second quadrant and cos is negative, so this would be negative cos 10, but it is all squared. That is why it became positive there, because it's negative all squared, so it becomes positive. So we get a mark for this as well. And then from there, cos of 360 minus is in the fourth quadrant, and the cosine is positive in the fourth quadrant, so this becomes positive. Right, let's continue with our work here. You can see we have the tangent here, which we can change to sine divided by cos. Sine 10 divided by cos 10, and then from there you can see one of this cosines here, would be divided out there. So we will be left with here, if I go to that side here, we'll be left with, because the cosine is divided, we got 1 there, so it's sine 10 divided by 1, which is sine 10. One of the cosines there was gone, so we have cosine 10 divided by the cosine of 70. Now, continuing with this, we can see that now we can change this one here, the cosine of 70. We can change it to a sine using the reduction formula, because cosine of 70 is the same as cosine of 90 minus 20 degrees, which means this changes to the sine of 20 degrees. So that is why I wanted to change that to a sine, because I would have seen here that I have sine 10 cos 10, which means I am taking it from this formula of sine double theta, which is 2 sine theta cos theta. So if I have sine 10 cos 10, if I have this as 2, I have this as sine 10. I want to take it, remember I have sine of 2 theta, which is 2 sine theta cos theta. But in my case, I have 10, sine 10 cos 10. So what am I missing? I'm missing the 2 here. So what am I going to do? I'm going to introduce it strategically by taking half times 2, which means that I can have now a half times 2. Now you can see that now this guy looks exactly like that one. So it's 2 sine 10 sine theta cos theta sine 10 cos 10, which means that now sine, what is our theta? Our theta is 10. So this means that this would be sine of what? 2 times what? 10. So that is why there we then going to have the sine of what? The sine of 20, because 2 sine theta cos theta, or 2 sine 10 cos 10, congests to sine 2 times 10. It's double the angle. The angle is 10. We've doubled that. So we can see that now everything is, or sine 20 and sine 20 are going to divide out. We'll be left with half as our solution set there. So that's how you were supposed to go through that particular problem. Right, good people, we move on now. We want to touch on aspects of now identities. We want to touch to aspects of identities. Let us go through how we should prove identities. What is an identity? An identity here, you can see by definition, we are saying an identity is any mathematical statement, here that is true for all values of the variable, excluding the values where the identity is not defined. So it is a mathematical statement that is true for all values of a variable, excluding those where it is not defined. And when we prove identities, we always work with two sides, the left-hand side and the right-hand side, denoted LHS and RHS. Separately, and simplify and manipulate the two sides till they are equal to the same expression. In grade 12, compound and double angles are included in this topic, and hence strategies to use these compound and double angles would be discussed in the slide to come. Now let us look at that. How do we prove identities? Useful tools. We split the left-hand side and the right-hand side. That is the first thing that we do. And then we use basic identities where tan is sine divided by cos of an angle, and the sine squared of an angle plus the cosine squared of an angle is equals to 1. And then we can use the double and compound angle formulae for addition and subtraction of fractions. Remember the LCD, and sometimes we may need to use the conjugate, which is very important. At times we will also need to factorize. Highest common factor, difference of two squares, trinomials, grouping, sum or difference of two cubes. Very, very important. At times we would need to factorize. Express all the terms in the expression as sine and cosine of angles. So that is the first thing that we need to do. We express everything as sine and cosine before we start simplifying, which means if you are given the tangent, you need to change it to sine or divide by cos. Right, now, additional formulae that are useful. I want to discuss with you the additional formulae. Please make sure that you use them, note them and use them for problem solving. They will help you a lot when it comes to identities. From the square identity, the square identity sine squared theta plus cos squared theta is equals to 1. From here, we can make sine the subject. The sine squared of theta is 1 minus what? The cosine squared of theta. That's one thing we can do. We can also make the cosine the subject. Cosine squared of theta is 1 minus the sine squared of theta. But if you look at this, there's something extra that we can do. There's something more that we can do. Zoom into this, you can see that we have what we call a difference of two squares, where if we have a squared minus b squared, this is equal to a minus b, a plus b. Also here, 1 is the perfect square, the cosine squared of theta is the perfect square. So this can also be simplified as 1 minus cos theta into 1 plus cos theta. So this should always be at the back of your mind when you work with identities. We can do the same here, 1 minus sine theta into 1 plus sine theta. At times, this is necessary when you are simplifying compound angles, or when you are simplifying identities, when you are proving identities, I should say, not simplifying them. Right, now, this is what we can get from the square identity. We can get formula 1, we can get additional formula 2 from the square identities. Now, from the cosine double angle, if you look at the cosine double angle, the cosine double angle can be written as what? The cosine of 2 alpha is the cosine squared of alpha minus the sine squared of alpha. This can also be written as the cosine of double alpha 2 cos squared alpha minus 1. It can also be written as 1 minus 2 1 minus 2 sine squared alpha. Now, if you look at these two, there is nothing more that you can do in terms of factorization. There is nothing more that you can do. But if you look at the first one, the cosine of 2 alpha as cos squared alpha minus sine squared alpha, this is still a difference of 2 squares. So we can write this as cos alpha minus sine alpha into cos alpha plus sine alpha. So this now becomes what? It becomes our additional formula 3. It becomes our additional formula 3, which is something you should always be thinking about when you are proving identities. Now, there is another one. If you look at the sign, this is what I call the hidden 2 sine alpha cos alpha. This is what I call the hidden perfect square trinomial. Now, with this one, I want you to check and notice in some of the problems on identities, you will be given 1 plus sine of double alpha. If it happens that they give you that, please do think about what I refer to as the hidden perfect square trinomial. I'll show you how it works, but I need you to always be vigilant when you work with identities, because at times you'll find that you are supposed to be using this concept where you are extracting the hidden perfect square trinomial. How do you go about that? We are going to use this identity that I'm putting on a block there. You see 1, there is 1 there. 1 can be written as what? Sine squared plus cos squared. So I am going to change 1 and write it as cos squared of alpha plus sine squared of alpha plus 2 sine alpha cos alpha. I am taking the 2 sine alpha cos alpha from the double angle of what? Of the sine trig ratio. Now, I can write this as, I can put the squares on the extreme, cos squared alpha plus 2 sine alpha cos alpha plus sine squared alpha. If you look at this, if I can just squeeze in something here, if I can let if cos alpha can be A and sine alpha can be B, notice what will happen. I'll have A squared plus 2AB plus B squared. Now, if you are to factorize this, you will get A plus B, A plus B. If you factorize, then this becomes what? A plus B squared. So it reduces to what we call a perfect square trinomial, which you learned in grade 10. So now what I'm going to do here is I am going to factorize just like I did with the one for A and B. I will have cos alpha plus sine alpha, cos alpha plus sine alpha. This is the same as the cos alpha plus sine alpha all squared. So this is the perfect square trinomial that was hidden, and we will call this the additional equation 4. We will refer to it as the additional equation 4. So you have now 4 different equations that are additional to what you know, that have been derived from what you know, that would be useful when you prove identities. Right, let's go to application now. We are now going to prove identities. Let us go to the application question now. In proving these identities, let us use the basic principles that I spoke about. I said if you have any tangent, you're going to change it and write it as sine over cos, because everything should be written as sine divided by cos. Now, let's look at first the solution side. I am putting in the formulas that will be useful there from the formula sheet. Now, let's look at how we can start with this. Start with the right hand side. I changed a tan to sine over cos because I said I want everything to be written as sine and cos before I can simplify. Then I can go to the left hand side. Now, in my left-hand side, I have the double angle for cos. And you can see here that there are 3 equations for the double angle for cos. I need to be able to choose the correct one. Now, if you look at your right-hand side, on your numerator, you have sine, which means when you've simplified everything here, everything in this block here, you should be left with what? Sine. That is how you should simplify it. You should simplify it such that you are left with sine, because that is what the right hand side is saying, which means you are going to change the double angle for cos and write it in terms of sine. So which means you'll be taking this one. That is why I used 1 minus sine squared of x. And then minus the sine of x. And then from there, obviously, the sine of 2x will always be written as 2 sine x cos x, like that. So I wrote it as 2 sine x cos x. So in simplifying that, I get 1 minus 1 when I open the bracket and distribute. 1 minus 1 plus 2 sine x minus sine x. Simplifying that further, I get that 1 minus 1 is 0. I'll have 2 sine squared of x minus sine x. In the denominator, I have 2 sine x cos x minus cos x. So you can see now I can take out a common factor of sine x here. So that is why I took out sine x. I'm left with 2 sine x minus 1. On the denominator, I can take out also a common factor of cos x. So I'll be left with 2 sine x minus 1. So these two are going to divide out, and you'll be left with sine x over cos x, which is obviously the same as what we got here. So we can see that now the left-hand side is exactly the same as the right-hand side. So that is how you prove that identity. Right, good people, we move right along. Next one, this one is an activity for you. I am going to give you just a sweet 5 minutes, just 5 minutes for you to simplify that identity, or for you to prove that identity. Please work as quickly and as best as you can. Your 5 minutes time starts now. Right, hello and welcome back. I hope you were able to work with this problem. This is a very nice problem because it infuses everything that we spoke about when we were deriving our additional formula. It infuses it very nicely because you can see here we have 1 plus, and I did speak to you about 1 plus the double angle for sine, that it takes us to the hidden a perfect square trinomial. And here you can see we have the cosine of a double angle, which means we have to visit the double angle formulas for the cosine and check which one, because there are 3. We need to know which one to choose. What would be our choice based on? It will be based on what we have to prove. It will be based on the side. You can see on the numerator, we want cos minus sine, which means when we choose to change the cosine, we need to change it such that we choose the formula with both the cosine and the sine. So we need to be very, very strategic here, and we'll be able to enjoy our identities. Now let's check. I'll first start by flagging our formulas that are very famous formulas that we use here that will help us there. All right, let's see. Now if we check on the first step, what did I do? I was informed by this. I was informed by this that I need to change cos and take the formula for double angle for cos, take the one that has both cos and sine, because on the right hand side in the numerator, after I've simplified, I need to get cos and sine. So I simplified it to cos squared minus sine squared. So you can see that here there is what we call the difference of two squares. We spoke about this. We spoke about this, and now I am bringing in, for one, I am bringing in sine squared theta, or it's alpha, plus cos squared alpha. I am bringing that in, cos squared alpha and sine squared alpha, to replace one, because I know and appreciate that there exists a hidden perfect square trinomial. So what do I do now? I simplify the numerator using the difference of two squares that I showed you on the additional formula that you'll need. And then from there, I simplify the denominator using the formula that I showed you for factorizing the hidden perfect square trinomial. Now you can see beautiful here that this will beautifully divide out, and then from there I'm left with cos minus a sine of an angle divide by cos alpha plus sine alpha, which is the same as what I had on the right hand side. So you were able to then prove this identity very much strategically. Right, we are moving on. There's another activity, but I'm looking at the time that is left. It's too less, so I am going to take you through this. I am going to do this together with you. Now, if you check here, we have cos 5 theta, cos 3 theta, cos 5 theta, sine 3 theta. One can see that there's something happening here. One can see that there is an expanded form of the compound angle. This is the expanded form. Remember in the previous lesson last week, we showed you how to expand as well as how to congest. Now you can see here we need to be able to apply what we did. So we see an expanded form of the compound angle, but we need to use our formula sheet to check which one it is. You can see it's cos cos, sine sine. So we go for cos cos, sine sine. It's either this formula or that formula. Now let's check what will determine the sign. This is positive, which means that it is exactly this formula there. So if it's cos of an angle, cos of the first angle times cos of the second angle plus sine of the first angle times sine of this second angle, this must be reduced to what? Cos of the first angle minus the second angle. So let's go there and see. You see, I took the cosine of the first angle minus the second angle, because if I were to expand, it will take me directly there. And then from there, moving right along, it gives me the cosine of 2 theta. And if I look at the right-hand side, obviously this is divided by 1. I can see on the numerator I must have cos and sine. So I must then choose the correct formula here out of these three. Correct formula that has both cosine and sine. So in doing that, I am going to choose the one equation here. So I am going to change cos 2 theta to what? Cos squared of theta minus sine squared of theta. Still here, I can have the difference of what? Difference of two squares, the difference of two squares. So in reducing that, I can then apply the difference of two squares formula, and then from there, I can actually then divide again, which will give me the value which is the same as the right hand side there. So I think that is sufficient. We move on. Now we move on to the general solution. As I alluded when I started with this lesson, that there are two methods to use. It is the graphical method and the quadrant method. For the purpose of this lesson, I am going to be using the quadrant method, and I'll be consistent with the use of the quadrant method. But remember, other educators taught you to use the graphical method. If that's how you were taught, please stick to it. It works best as well. It works as much as the quadrant method would work. Now, in grade 11, we learned how to solve trig equations. Let us now revise the basic concepts. Number one, to determine the general solution of a trig equation in the form of sine theta is A, cos theta is A, and tan theta is A. What do? We calculate the reference angle. Let me go back here. And then from there, we are going to use the arc sine of A, which would give us the reference angle there. We do the same with the cosine, we do the same with the tangent. The general solution of a trig equation represents all possible angles in degrees that satisfy the given equation. Since trig functions are periodic, solutions repeat at regular intervals. You will see when we do our trig functions, you will see how these points of intersection repeat themselves at regular intervals, and those regularities with which they occur can be simplified in terms of the general solutions, right? Now, we are going to do the following. We calculate the angle by applying the arc sine, the arc cosine, and the arc tangent of the numerical value of A and ignoring the sine. I think we spoke about that in the previous slide. Look at the sine of A and the given trigonometric ratio and determine which two quadrants the solution must lie according to the cast diagram. And then from there, the form sine theta is equals to A and cos theta is equals to A. The value must be in the interval -1 and 1, because you remember the sine function has an amplitude of 1. So it ranges, the range is between -1 and 1. Similarly, the cosine function also ranges between 1 and 1. So we need to note the minimum value is -1 and the maximum value is 1. For the tangent, A can be any real number. It has no amplitude. Right, the types of general solutions. Let's quickly discuss the types with which the general solutions may exist. The first one, the trig ratio is equal to a constant. If that is the case, then it's simple. You are going to get your reference angle by taking what? Theta should be, or rather the reference angle should be what? The arc sine of 0,3. Then you go to your general solution. You can do the same here. You can say that now with your reference angle, you would have that it is equal to what? The arc tangent of -2,5. Or rather the arc tangent of 2,5, because we ignore the sine. Right, we are moving on. Type 2, equations of the form A sine theta is equals to B cos theta. In this type, the angles should always be the same for you to apply this knowledge. So what do? This changes to the tangent. So you have that this is A sine theta is equals to B cos theta. What you do is you divide both sides by cos. Cos theta, cos theta. You have that this is A tan theta is equals to B, which means that the tangent of theta will be equals to B over A. So you've changed this to what? To the tangent. So this is what we call the tangent type. How do you see it's the tangent type? You must have the sine of an angle and the cosine of the angle, but the angle needs to be the same. So you can do the same with this one. I'll just take you through this. 3 cos theta is equals to 2 sine theta. We divide both sides by sine theta. Divide by sine theta. We are left with now 3 tan theta is equals to 2, which implies that the tangent of theta would be 2 divided by 3. Then you proceed. You can see that now it looks like what? It looks like a type 1. You can proceed and solve that, determine the general solution. Right, type 3, equations of the form sine alpha is equals to sine beta, cos alpha is equals to cos beta, tan alpha is equals to tan beta. We are equating the same trig ratios that contain different angles. So what is the methodological approach there? We are going to be dropping the trig ratio, or correctly said mathematically, we are going to be equating the angles there. So this to solve equations of this form, we equate angles by dropping the ratio. So which means here, because we have sine and sine, the angle is alpha plus 10, the angle is alpha minus 10. So our reference angle comes from alpha plus 10 is equals to alpha minus 30. And then from there, we will proceed to try and solve for that one. Right, let's move on here to type 4, which is the cofunction. To solve the equations of this form, we need to change the sine to a cosine and the cosine to a sine. So now, how do you see that it's this type? You have the sine equated to the cosine, right? Remember, at times when the angle is the same, if it was 2x and 2x, we're going to change it to the tangent because the angles are the same. But because this is not the same trig ratios, the angles are also different. We want to make it this type. But for us to do that, we can change either sine to cosine or cosine to sine. So we can change the sine. If we change the sine to cosine, we can write this as the cosine of 90 minus 2x. This would be the cosine of x minus 10. Now it looks like a type 3 problem. We can have 90 minus 2x, which is x minus 10, and we proceed to solve from there. Or alternatively, you can change the cosine to sine. So this would be the sine of what? 90 minus what? X minus 10. Simplifying this gives us sine 2x, which is the sine of 90 degrees minus x plus 10. So this is 2x is equals to 100 degrees minus x. Then you can simplify from there, because remember it's sine and sine, so we can apply the knowledge that we learned from type 3. Right, I'm going to the last type, that is type 5. Type 5 are those that involve factorization. You should be able to do that, but it is important for you to revise grade 10 and 11 factorization concepts. Right, now we can look at this and we can say, if you look at this, you have 2 sin x cos x minus 6 sin x minus cos x plus 3. There are 4 terms. Immediately when I get more than 3 terms, I would think about grouping. So if you are to group these two here, you can see that 2 sin x is common. So this would become 2 sin x for the first 2, and then I'll be left with cos x minus 3. I can do the same with these 2. I can take out a negative sign. I'll be left with cos x minus 3. And then you can see now that I'm factorizing by grouping. So I'll take this as cos x minus 3, and then I open the new bracket sin x minus 1. So I can proceed to solve here, saying cos x is equals to 3 or sin x is equals to half. So this has taken me back to type 1. So that's what you need to be able to do. Also here, you can see that this thing here is the same as what? If you let sine theta be x, this was x squared minus x minus 2 is equals to 0, which can be simplified to x there, 2 and 1 minus and plus. So it means that if you bring back the sign, it's sine theta minus 2 sine theta plus 1. So you can then simplify this further. So those are the things that you need to know. I've exposed you to 5 types. Please go and look at them. Try to understand what is expected of you from each type before you can solve general solution questions. Right now, I want to take you through 2 problems. I will be taking you through 2 problems. Because of time, I am not going to give you any activity on the general solution. I'll just take you through the problems as examples, and then I'll conclude today's lesson. Let's start with the first one. Determine the general solution for cos theta minus 24 is 0,715. This is a type 1. Now let's check. Obviously, the cast diagram plays a role here because we are going to be locating quadrants. Now, first things first, we want to find the reference angle. How do we find the reference angle? We will take the arc cosine of this, which then simplifies to what? 44.37. Now that we have the reference angle and we see that this thing was positive, we're going to locate where cos is positive. It is positive in the first quadrant and also positive in the fourth quadrant. So the reference angle will take care of the first quadrant. Let's check now. We are looking at this, locating it in the first quadrant. In the first quadrant, we get that the angle to theta minus 24 is 44.36, which is the reference angle, plus K360. When we simplify that, we get that this is 68.35 plus K360, and K is an element of integers. That is the solution we get in the first quadrant. Now we need to locate the solution in the second quadrant, or rather in the fourth quadrant, I should say. In the fourth quadrant, quadrant 4, what do we see here? We know in quadrant 4, we must say 360 minus. So that is why I used here 360 minus the reference angle, because in the fourth quadrant, the instruction is 360 minus. When we simplify that, we get that this simplifies to 315.64 plus K360, and then when we transpose the 24, we get that this is 339.64 plus K360. So we were able to locate the solution in the first quadrant and locate it in the fourth quadrant, because cos is positive in the first quadrant and in the fourth quadrant. Why are we doing that? Because we are using the quadrant method of determining the general solution. Right, let's move on. Now, this was supposed to be your activity, but I am quickly going to take you through it. Now, first things first, here with our solution set, we look at the cast diagram. Now, if you look at this problem, I just want to take you through something here as far as this problem is concerned. If you look at this problem here, you can see that in this problem, we have a cosine and a sine, and the angles are the same. So because the angles are the same, this will change to a tangent. So if we go to that, we can see that it's equals to 0. This was supposed to be equals to 0. And then when we transpose the sign, we get that this is 2 sine x. And then we divide by the sign. So this would be 3 cos x divided by sine x is equals to 2 sine x divided by sine x. So this would give us the tangent of x. Then we locate the quadrants. We find the reference angle first, which is 53.61. So since this was positive, we know tan is positive in the first quadrant and also in the third quadrant. So we are going to locate the general solution in the first quadrant. Let's go here. In the first quadrant, that's what we get as our general solution, and also locate it in the third quadrant. Remember, in the third quadrant, we need to say 180 plus the reference angle. So this would be 180 plus 56.31, which leads us to, obviously here, just a minute here, I ran out of battery here in my pen. Right, so we just indicated that we are locating the quadrants. In the first quadrant, we have 56.31 plus K360. In the third quadrant, we have 180 degrees plus the reference angle plus K360. So we are going to add the two, and then from there we get our general solution. Right, let's go through that. We get that this is 236.31 plus K360. Remember, this is important. It should appear at least once in the problem that we are solving. That K is an element of integers, because if it's not there, you are going to lose 1 mark. Right, let's go to the last problem here that I will do with you. I'm interested in doing one that involves what? That involves factorization. Let's check now, activity 5. Now, if you look at this one, they say determine the general solution for cos 2x minus 3 cos x is equals to 1. So you can see the angles are different. We have the sine and the cosine. Even if you can transpose that, you will still have 1 plus 3 cos x. So this is a trinomial. So we want to know how to actually reduce, but remember, we have at our disposal 3 formulas that we can use to change the cosine. What are they? 1, 2, 3. We need to choose one. What would advise us, or what would actually lead us into choosing the correct one? We check this term. It's the cosine of x. So if we choose, we will choose one that is written in terms of cos only, because we want to factorize. So we will choose this one. So we go with that problem. We've chosen that one. We are writing cos 2x as 2 cos squared x minus 1. And then we simplify further. We get that this is 2 cos squared x minus 3 cos x minus 2. So if you are to try and say, I want to check the existence of the trinomial here. So I'll let cos of x be equals to a. If I do that, what will I have here? 2a squared minus 3a minus 2 is equal to 0. You can see this is a trinomial that you know from grade 10 and 11. Now, let's simplify that. Now we can get factors out of that trinomial. 2 cos x plus 1 cos x minus 2. Or you can use a quadratic formula from there to simplify your work there. Now, looking at that, we get that cos x is negative half and cos x is equals to 2. If you check here, I said this one is rejected. Why am I rejecting it? Remember, we said the cosine of an angle should be trapped between -1 and 1. Why is that? Because the cos graph oscillates between -1 and 1. It has a maximum value of 1 and a minimum value of -1. So we reject this one. Even if you put it in your calculator as a type 1, it will say math error. Now we are going to proceed with this one. We find the reference angle by ignoring the negative sign, because this negative sign is going to tell us about the quadrants. It is telling us that cosine is negative. So where is cos negative in our cast diagram? It is negative in the second quadrant and also in the third quadrant. So we're going to locate our general solution in the second quadrant as well as in the third quadrant. Right. Now this will then take us to what? The second quadrant. What happens in the second quadrant? We need to use 180 minus. So it will be 180 minus the reference angle. Let's go through that. 180 minus 60 plus K 360. And then from there, this simplifies to 120 degrees plus K 360. We are done in quadrant 2. We need to go to quadrant 3, as I indicated there. So in quadrant 3, what is the instruction? 180 degrees plus the reference angle. So we take it to 180 plus 60 plus K360, and then if we add the 2, we get that it's 240 plus K360, and we know K, an element of integers, should appear at least once in that particular problem, and then from there we know that we are going to get all our marks. Right, that would conclude our general solutions, and then now we need to, if we can perhaps go back, you see we are using K360 here because we are working with sine and cosine. If we are working with the tangent, we're going to use K180 because the period for the tan function is 180 degrees. We do everything exactly as we're doing it, but we are going to use K180 as the periodic shift there. Right, let's look at the summary of the lesson to conclude. To be competent in trigonometry that we did today, one needs to understand the reduction formula and infuse the compound angles there. One needs to know how to solve numerical reduction problems. We did that. One needs to know the formula derived. This is very, very important. It helps you with identities. The formulas that I derived from the compound angles and the double angles, from the double angles as well as the square identities. We did find some difference of two squares and a hidden perfect square trinomial. We should also know how to prove identities. We should also know you are competent if you know how to work with the different types of the general solutions, just to know how to address each general solution type, and then you should know how to solve general solution problems where compound and double angles are infused. Now let's preview the next lesson. What is it that we'll be looking at in the next lesson, which would be next week? We will be looking at trigonometry 2D and 3D, and that would be on the 19th between 2.5 past 3, trigonometry 2Ds and 3Ds. So for today, we are calling it a day. Thank you very much for watching. Please take care of yourselves and take care of each other and practice mathematics. Goodbye.